What is going on, guys? Welcome back. In this video today we're going to use TensorFlow and neural networks to predict the next word of a given text sequence, and we're going to use that mechanism to generate text with this AI. So let us get right into it. Now, before we get to the actual video, I would like to mention that this video is sponsored by Bixly. And don't skip this part because this could be quite interesting to some of you guys working on software projects. Oftentimes, software projects are quite difficult to finish, and Bixly can help you with that. They have been successfully completing projects on time and on budget since the year 2008, so they have a solid track record of successful completion with the money they have, with the time they have. And they offer multiple different services. You can go to their website. You will find a link in the description down below, bixly.com/nn for Neural 9. And you can click on their services tab, for example, to see what they offer here. They have different services like no or low code type of services, enterprise development, DevOps, mobile development, and more. You can take a look at that. And if you need some help getting your project finished on time or getting it done right the first time, you can talk to the people at bixly.com. As I mentioned, you will find a link in the description down below, and they have a solid track record. And in addition to that, you can also get a free consultation by visiting their website on the link in the description down below. Alright, so we're going to build a text generating AI in this video today, and to be precise, we're going to build a neural network that always predicts the next word given a certain text sequence. So for example, we might have 10 input words, the start of a sentence, and our model will always predict then the 11th word, or maybe it will give 10 suggestions for the most likely next word. And this can be used, first of all, of course, just for the next word prediction, for auto-completion or something. And it can also be used somewhat, at least, for text generation. We can attempt to do text generation with that because the act of text generation is just always predicting the next word and the next word and the next word and the next word. There's not much more to it. This is what we're going to do in this video today. We're going to do that with TensorFlow. We're going to build our neural network with TensorFlow. In addition to TensorFlow, we're also going to use NumPy, Pandas, and the Natural Language Toolkit, NLTK. Those are the libraries that we need to install, and we can do that by opening up the command line and typing pip install TensorFlow, NumPy, Pandas, and NLTK. And we're going to need NLTK because, of course, in order to train our model, we need to work with some text data. So we need to have some raw text, and then we need to tokenize it and stuff like that, which is why we need the Natural Language Toolkit. And the dataset that we're going to use in this video today is going to be the fake news dataset that you will find at the link in the description down below. You just go to this GitHub repository here, you click on the data directory, and here you have this fake or real news CSV file. This is just a simple dataset containing news articles. Some of them are fake, some of them are not fake, but at the end of the day, all of them should have coherent sentences. So we can use them to predict next words. And you will see that the dataset you use is going to be influencing the text generation. So if you use this dataset, you will get a lot of information about presidents and some political stuff, whereas if you use a Shakespeare dataset, you're going to get some more poetic text. But yeah, you need some dataset. You don't have to choose this one. All you need is you need to have a string in Python. You can store this string in a variable text. So just have something text equals, and then you need to have a lot of sentences here. So you should have like 100,000 characters, 1 million characters, whatever, where you have sentences so that you can see a lot of examples where you have one word following the previous words. This is what you need. We're going to get this from the fake or real news dataset. But let's start with the imports now. We're going to import random. We're going to import pickle. We're going to import NumPy as NP. We're going to import pandas as PD. We're going to import matplotlib. Actually, we don't need matplotlib. We need nltk.tokenize, or actually from nltk.tokenize. We're going to import a regular expression tokenizer, so regexp tokenizer. We're then going to import TensorFlow, or actually let's do it with the from imports from TensorFlow. From TensorFlow Keras models, we're going to import the sequential model, and we also want to import the load model function. We also want to import from TensorFlow Keras layers. Here we want to import LSTM. Dense layer. So LSTM is basically a recurrent neural network layer, long short-term memory. And this is what you want to use for stuff like next character prediction or even stock prediction, stock price prediction, or next word prediction. This is a very useful layer for this. The dense layer is just a fully connected basic layer. And then we also want to have an activation layer. And then we want to also say from TensorFlow .keras.optimizers, we want to use the RMS prop optimizer. Those are now the inputs. For the text, it's quite simple. We're just going to load the text data frame using pandas. So read CSV. We're going to load this fake or real news CSV file. And we can then print this. And you can see that it's a basic data frame where we have the title, the text, the actual news article, which is what we're interested in, and the label. Now, since we're not going to do fake news detection, we might do that in another video soon. But we're going to just focus here on the raw text. We don't care about any machine learning prediction task here, other than the next word prediction. We don't want to know if that's fake or not. We just want to get the text and predict the words in the text. So what we're going to do now is we're going to say that the text is going to be a list of the text df.text value. So we just take all these texts, the list, basically, we turn this into a list. And what we do then is we say the joined text is going to be white space on this white space character, join all these texts. And now I'm not going to print that because that's going to crash the notebook because it's just too much text. But this is now just raw text. All these articles, one after the other. That's the basic thing that we have here. And what we can do now to not, train them all for too long before it actually works. Let's just go ahead and train them all on a part of the text. Oftentimes you will not be able to do it on all the text anyways, because you're not going to have enough RAM to store all of this. So what we want to do is we want to say partial text is going to be equal to joint text. And we're going to say up until 10,000 characters, just for testing purposes here. Now, what we want to do with all of this text is we want to tokenize it. So we want to say that the tokenizer is going to be a regular expression tokenizer, and the regular expression is going to be quite simple, just words. Just tokenize the individual words, and the tokens are then going to be tokenizer, tokenize, and we're going to just tokenize the partial text. Now, to keep things simple, to not have too many different words, and to also be a little bit tolerant with different cases, we're just going to say here that we want to tokenize only lowercase. So we're not going to care about uppercase or lowercase characters here. Everything is going to be a lowercase, and the generated text is also going to be lowercase. So those are the tokens. Now we can print the tokens probably. There you go. So it's just a list of the individual words that we have here. And what we want to do here is... what we want to do here is we want to say unique tokens are going to be equal to numpy unique, so that we don't have duplicates, tokens. And what we want to do now is we want to have a dictionary so that we can match a token to a respective index. So when we have a word, we want to know what's the index in that list. And for this, we're going to say unique token index is going to be a dictionary where a token is mapped to an index for index token in enumerate unique tokens. That's what we want to do here. So maybe we can look at that. There you go. Each word that we have is going to be mapped to a certain index. All right, so that's what we have here as a basis. Now, what we want to provide here is a parameter, or at least we want to know this information. You don't have to store it in a variable, but we want to have some number of words that we want to look at. So how many words do we want to look at in order to predict the next word? Do we just want to look at the last word and then predict the next word? This is not very useful because you don't get any context. If you look at the last 1,000 words, maybe you get too much context. So let's just go with something like 10. Let's say n words is going to be equal to 10. And then we're going to have a list input words, and we're going to have a list next words, and this is going to be just a structure for X and Y. X is going to be the input words, Y is going to be the next words. So for each position in our text, in our joint text here, what we want to do is want to get 10 words. We're going to put those 10 into input words. We're going to get the 11th word, which is going to be the next word, and then we shift by 1. So we're going to get the next 10 words. So all except for the last one is going to be are going to be the same in different positions, of course. And the next word is going to then be the 11th word after that sequence. And we're going to do that for each position in our text, and this is going to result in our training data. So we're going to just do it like that, and we're going to say here for I in range, length tokens minus n words. Now we're not going to iterate over the joint text, we're going to iterate over the tokens, because here we tokenize for a reason, because we then have similar words grouped into a token. And we say here minus n words, because of course we don't want to go until the end, because then we don't have any words to predict anymore. For range length tokens minus n words, what we want to do is want to say input words append, and we want to append all the tokens from the respective index starting at 0 up until that index plus n words. So we're just looking at the 10 words after the current position, and the next word is going to then be the 11th word. So it's going to be tokens I plus n words. There you go. And this needs to be plural. There you go. Next words is always one word, and input words is always a collection of 10 words. So you can see here Daniel Greenfield, a Shillman Journalism Fellow at the Freedom Center, and then the next word would be is, right? And then is a New York writer focusing on radical and so on. That's the basic idea of what we're going to do here. And now we want to turn all of this into X and Y. So we're going to say X is going to be a NumPy array full of zeros with the following structure: length of input words, n words, and length of unique tokens. The basic idea here is that we want to, for each sample, we want to have n input words and then the actual, then a Boolean for each possible next word. So we want to have basically for each sample, so we have input words, the length of input words, amount of samples, then we have the 10 input words, and then we have for each token that we have, for each unique token, we have either 0 or 1 if it's the next word or not. So we have this bag of words structure where we have for each token a binary feature, and all of them are going to be 0 except for one. It's going to be 1. The next word is going to be 1, and this is how we're going to pass this to the neural network. And the data type for this is going to be a Boolean. That's that. Then for the Y, we're going to do something similar. We're going to say NP zeros, but this time we're going to say length next word. Basically, should be the same. Length unique tokens, because here we don't need input words. So what we do here is for each sample, we just do the same thing. What's the next input word? Sorry, my mistake. Here we have only one set to 1. Here we have up to 10 set to 1, up to n words set to 1, because what we have here is we have basically the input to the model. So what are the tokens that are activated? And then we have, let me rephrase that. What we actually have in the X array here is we have for each sample, so for each selection, we have n different, so 10 in this case, 10 different bag of words where only one word is set to 1. So you have basically 10 words, but you don't have 10 words as strings. You have 10 words represented as a bag of words where you have just one index, one position being set to 1, all the other to 0, but you have that 10 times because you have 10 different words. And here you just have this one one time, because you have just one next word to predict. I hope this was not too confusing. I made some mistakes in the explanation here. Here, of course, we also need dtype equals bool, but what's the problem here? Module numpy zeros. There you go. Next word is not defined. Why do I keep using this form? It's plural. There you go. So x now looks like this: false, 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 and the word that is used will be set to true. All the other fields are going to be equal to false, and y looks like this. You have the same structure, but you only have it once because you only have one single word. That's the basic idea. Now, what we want to do here is we want to say for index and words in enumerate input words, we want to say also for j word in words, or enumerate words, we want to say that, because this here, what we have here is just a structure. And now we want to fill up that structure with the actual values. So we want to take the position, the current sample, the current word, and we want to get the word at this position and map it to the respective index, which is done by the dictionary that we created, and want to set that position by 1. So again, let me put this into somewhat simple terms. We have the structure that I just explained, and what we do now is we go through all the samples that we have in input words. We go through all the words per sample, and then we go in the X array, which is our input to the neural network. We go to the sample position. In that sample position, we go to the word that we're currently looking at, and then we take that word, map it to the respective index, find that index inside of the array that we created, and set only this position to 1, or true if you want. Doesn't matter. And for Y, we do something similar, but we skip the J part, because we only have one word. And here we need to also use next words I, because that is what we're looking at. We're not looking at this word, but at the next word. All right, so, and of course this obviously is not done inside of the loop. This is done only once. And that should be it. Let's see. Now we're not going to see the results probably because we only see the false instances here, but now we have the values actually in our arrays, in our X and Y arrays. So that's basically it. Now we can go into training the model. And for this, we're going to have a very simple structure. We're going to say model equals sequential model. We're going to say model at simple LSTM layer, 128 neurons. The input shape is going to be n words, depending on what this variable is. Then we're going to have the length of the unique tokens. And we're going to say return sequences equals true, because what I want to do next is I want to add another LSTM layer. And if you have multiple of those, you need to add this return sequences to all but the last layer. So since I'm going to have two, I'm just going to say LSTM 128 here. We don't need to return sequences here. And then we want to say model at dense layer, and we're going to say length unique tokens here. And we're going to say, finally, we want to have an activation layer with the softmax function. So each word will have a certain probability, which also makes it easy for us to see, okay, if we don't want to take the best option or the most likely option, maybe the second most likely option is the right result. So we can filter for the n best solutions, the n best predictions. That is the model. Input shape is not defined. What did I do wrong here? Input shape is not defined. Oh, because it's not a function, it's a parameter. There you go. Model.compile. We're going to compile using the categorical cross entropy, since we are predicting using the softmax function here, multiple categories. The optimizer is going to be equal to an RMS prop optimizer with a learning rate of 0.01. And the metrics that we want to look at are just the accuracy. And then what we can do is we can store, actually we don't need to store the history, we can just say model.fit x and y, and then the batch size is going to be 128. We're going to train for 10 epochs. You can also train for more than 10 epochs. And we're going to shuffle. We're going to set shuffle to true. And then we can fit the model if everything was done correctly. And you can see since we just used 10,000 characters, this is quite fast. We can also set this now to 30 epochs maybe. And we will get some decent accuracy on the test set or on the training set here. But that doesn't mean that our prediction, our text generation is going to be perfect just because the accuracy is high here. It just means that it's pretty good at doing this on the text that it was given. Now, we're not going to care about training the perfect model here. Let's just see how we would produce the results before we go into more detail on a better model or anything. Let's just say this is a good model. How would we then use it to predict the next word, and how would we use it to generate text? Now, first of all, we want to save the model. So we're going to save the model here into mymodel.h5. And we can also load the model by saying model equals load model. And then mymodel h5. We don't have to do this because we still have the model in our RAM. But if we want to load the model, we can just do it like that. And then we have the same model. Now, with this model, we can predict the next word by defining a simple function, predict next word. And we're going to have the input text here. And we're going to have the n best parameter, meaning we want to have the n best, the n most likely predictions. So what we want to do here first is we want to take the input text and turn it into a lowercase version of itself so that we don't have any uppercase characters because we don't have, we didn't train them all on uppercase characters, so it might confuse it or it will confuse it. We take the input text, we turn it into lowercase, and then what we do is we say the x that we want to feed into the model is going to be an array full of zeros with the following shape: 1, because we just have one input text, n words, and length of unique tokens. So basically the exact same shape as up here, but now we only have one input sentence or 10 input words, you could say. So we only have one here. And what we do now is we say for I word in enumerate, and we want to split the input text on white spaces. For each word in this text, what we want to do is we want to take this word and want to see if we can find it in our unique tokens list. So what we want to do is we want to say x0i unique token index for this particular word equals 1. And this, of course, can produce an exception. So if we don't find that word in our dictionary, this will basically tell us that there's a key error, we didn't find that word, so we cannot set this position to 1, and it will not predict the next words. How you handle that, you can think about this. So you can just, in the case of this problem, you can just say, okay, predict any word, or give me a random word, or maybe as an input use a different word. What we're going to do is we're going to just accept then, in this case it doesn't work, and in the text generation we're going to just go with a random choice, with a random word instead of the most likely word. But of course there are more intelligent solutions to this. So the predictions are then going to be, so this basically just creates again the bag of words with the respective ones in the positions. And then what we want to do is we want to say model predict x, and we want to get the result, so index 0 here. Those are the predictions, and what we want to do now is we want to return the n best predictions, and we can do that by using a NumPy function called argpartition. So np argpartition, we pass the predictions, we pass negative n best, and we get everything from negative n best until the end. That is our function, and this should now already work. So if I say possible is going to be equal to predict next word, and I can provide a sequence like I will have to look into this thing because I. Those are pretty basic words. I hope all of them occur. And let's go with the 5 best predictions. Key error, I. Okay, it doesn't know. Let's go with he. Maybe because we trained this on... Okay, it doesn't know because. Since, maybe. Since is also not known. Let's go with this thing and he. This should work. And now we can get the possible next words. Now here we get an array with indices. What you need to do in order to get the actual words, quite simple. You need to say print and then unique tokens index for index in possible. And of course we need some parentheses here. We just have to take the index and get the respective token from the list. And in this case, those are the 5 most likely words. He will have to look into this because he appearing, he made, he public, he at, he it. Those are garbage predictions because the model was trained on 10,000 characters. This is not much at all. But we can see that it makes predictions. And the more data you train a model on and the more complex the model is, the better the model is, the more accurate the predictions are going to be here. Now, before we look at a model that I trained already for quite some time, let's look at how we can use this now to generate text. Now, you can see since this prediction here is garbage, the text generation is also going to be garbage. But let's say it wasn't as bad as it is right now. How would we take this and generate text? Quite simple. We define a function, generate text, and we provide an input text that has to have the length 10. We provide n words. And we provide, I mean, actually we can take n words from above already. So let's maybe not pass this. And we provide a creativity. And the creativity is going to be set to 3. This is just going to be how many words do we want to choose from. We're going to make a random choice what the next word is going to be from the n best choices. What is this n? In this case, we're going to look at the 3 most likely choices and basically and choose from those. Now, we are going to use a parameter here, though. We're going to call it text length because we need to also specify how many words we want to generate. So we're going to say here that a word sequence is going to be input text split. We're going to split it on the white spaces so that we get a list of words. And we're going to then say the current position is 0. And now for placeholder in range text length. So for how many words we want to generate, we're going to say subsequence equals white space join tokenizer tokenize join the word sequence that we currently have in lowercase, obviously. And we want to take the current position up until current plus, now this is now plus n words, right? I think so. Should work. So this basically takes a subsequence, and now what we want to do is want to try to find the next word. We want to try to predict the next word, and this will not work, of course, if we have some unknown input. So what we can do here is we can say choice equals unique tokens random choice, and we're going to predict the next word from the subsequence that we're looking at, so from the last 10 words with the creativity that we're given here, so the n best words. We're going to choose from this list, and we're going to take that respective token. If some error occurs, for example, because we cannot find this respective key, we're just going to pick a random choice from the list of all tokens. So random choice all tokens. That's what we want to do here, and then whatever the choice is and whatever the choice or however the choice was made, we're going to just append this choice to the word sequence. And we're going to shift the current index by 1, And then finally, once we're done with this loop, we're going to join all of this on white spaces, and we're going to have some text that is going to not make a lot of sense, but it is going to be text. So let's go ahead now, copy this down here, and let's say generate text. This is the input, 100 is the length, and 5 is the creativity. Let's see what happens. He will have to look into this thing, and he public it whose KGB if woman political headline, whatever, right? So we get this text that doesn't make a lot of sense. You can already see that this is very political and stuff like that. So this is because it was trained on a news data set, fake news and real news data set. But this is how you can do this, here. Now, let's go ahead and use a model that I already trained on this data set for quite some time. I think I used 100,000 characters. So instead of using 10,000 here, I used either 100,000 or maybe even I used, I'm not sure if I didn't use 1 million. But I trained this and the results are not that bad. So let's see if we can get some better generated text here by saying model equals load model. And I stored it here in the pre-trained directory. So pre-trained model.h5. Or actually, I think it is pre-trained models, model h5. And I think then I should be able to just use these functions again. Let's see what we get here. Incompatible. Why is that? Oh, because I need to also load the same amount of data here. So let's see. Maybe I have to go through all of this again, but not the training part. And then, no, we get some problem here. Incompatible. Probably because I still didn't use enough. So let me add another 0. Let's go ahead and do this again. There you go. Now it does something. And hopefully, there you go. He will have to look into this because he makes, he could, he has, he is, basically also he is. Those are all reasonable predictions. So at least if you want to have something for auto-completion, if you want to have something for the next word prediction, this is actually decent. I still think that generated text will not make a lot of sense, but let's see what happens if we try to generate text with this. He will have to look into this thing, and he makes a replacement in our history. So even though it doesn't make a lot of sense what we write here, it is more coherent. The words, the words fit together at least somewhat. So this is actually kind of cool. Let's go ahead and try something else. Like I want to see what is possible. 1, 2, 3, 4, 5, 6, 7 in this world. I, you, it, we, is. So maybe let's go the president of the United States has announced 1, 2, 3, 4, 5, 6, 7, 8 that he will, he had, he's, he has, he is. Those are decent predictions. So for the next word prediction, let's go maybe with 10 to see what we get here. He would, he said, he could, he doesn't, he is, he was, he has, he had, he will. All of those are decent predictions. That is really, really good. Let's go ahead and see what kind of text it would generate if I provide that. And in this case, we get the President of the United States has announced that he will be more stressed of that is a former, this we will is president. Yeah, I mean, you can see it's better, definitely, but it still produces nonsense. Let's see how this changes if I just predict the best word every time. In this case, we would get only the best, the most likely solution. The President of the United States has announced that he is a good president of their children when the dreams application of the president when the president's sexually on the... Okay. And then maybe if we go with a creativity of 20, this will produce probably some garbage. But let's see, the President of the United States has announced that he did a president before his own the election he took out, and so on. So yeah, the text generation part is not too impressive, but the next word prediction part is pretty impressive. And of course, if you train this on more and more text on different data sets with a larger model, and you do this with maybe multiple days of training on a high-speed computer, this is going to give you some decent results over time. And yeah, this is how you can do that with TensorFlow with neural networks in Python. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, don't forget to check out Bixly, the sponsor of this video. You will find a link in the description down below to check them out. And as always, subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and